Okay. Bismillah ar-Rahman ar-Rahim. We will continue the topic. Topic was a steady state, right? Steady state. In previous class, we studied steady state in rectangular plates. So we studied the following problem. We have a rectangular plate, size B, C. So then equation is uxx plus uyy is equal 0. Then we have four boundary conditions, right? U0, U0y is equal f1y, uby is equal f2y. This condition with respect to x, and condition with respect to y, ux0 is equal f3x, and xc is equal f4x. So generally speaking, we may have here derivatives. That's why I just marked with red. We may have, or may not. If we have, then we call it second boundary value problem, right? So how we solve it? We solve it using separation of variables. And first we bring to 3 zero conditions. So we can split this problem into 4 problems. And each problem will be with 3 zero boundary conditions, and we solve it. So that was for rectangular plate. Now today we will change the shape of the plate. Shape of the plate, let be it is circle first. Let's say this is now our plate. Oops. Let's say this is circle. Let be this is x-axis. Okay. Then any point, circle has only one. Let's say radius is equal. Let be radius is equal c. Then we cannot proceed with the same equation. Because you remember when we studied heat conduction in the plate and also vibration of rectangle and circular membranes. In case of circle, we have to go to polar system, right? In polar system, the steady state equation, we can write like this: URR, because we know what is uxx and URR plus 1 over r, UR plus 1 over r square u theta theta. Let me write phi. Let me say, if this is a point xy, right? The same, I can call it as r phi. I'm not using theta because theta capital is like theta the same. So if this is a point ry, so what is r? R is this one. If I connect with origin, and this is the r, then this angle is phi. Then u phi is equal 0. This is steady state equation in polar system. Then we have only one boundary condition. What is the boundary condition? Boundary condition is function is actually ur phi, right? Not uxy, ur phi. So when r is c, so on boundary, when r is c, uc phi is equal, let's say, is equal f phi. So we are talking about steady state when on the boundary of this circle given heat is equal f phi. So we have equation and one boundary condition, equation in one boundary condition. And also we have so-called condition for U must be periodic, right? U R phi plus 2 pi is U R phi. Why? Because point R phi is the same as R phi plus 2 pi, right? If you change this phi to phi plus 2 pi, you will return back to the same point. So xy is actually the same as R phi plus 2 pi is the same, right? Phi plus 2 pi and R phi is the same. That's why U R phi plus 2 pi must be equal U R phi. It must be periodic with respect to phi, with period is equal to pi. That's a statement of the steady state problem for the circle plate. How we will solve? Now we can solve by separation of variables. So we will search solution U R phi in the form of R capital is a function of radius and phi capital the phi. The reason I'm using phi is this actually because sometimes students not differentiate when I write theta. If I use theta, then theta capital like this, and they're very similar, and sometimes they don't differentiate these two letters. That's why I better use phi maybe. It's better to use phi. So if we search like this, if you substitute into equation, what is URR? URR is R double prime times phi, right? Plus 1 over R plus 1 over R. So UR, what is UR? Is R prime times phi, right? Then we have 1 over R square, R times phi double prime. So this is the equation. When we substitute U here into this equation, we will get this one, right? Now I can multiply this equality to, let me multiply to 1 over, okay, I will multiply to R square over R phi, R times phi capital. Let me multiply this, both sides to this. So if you multiply the first one, so phi will cancel with phi, you will get R square, R double prime over R. Phi will cancel with phi. Next term will be plus R prime over R, right? Phi again cancel. Then what will happen with the last term will be phi double prime over phi is equal 0, right? Is equal 0. Now I can separate variables. Let me leave phi on this side, but R function shift to the left. Then I can write it like this: phi double prime over phi is equal minus I can write like this, all stuff like this: R square R double prime over R plus R prime over R. That's all, right? So left side is a function of angle phi. This is a function of phi, right? This side is a function of radius. Radius and angle, they are not related, interrelated. So these relations must be constant. And this constant, for convenience, let me denote by minus lambda. So I don't know what is lambda, but definitely I know that these two things must be constant, right? So then I will have two equations. One is phi double prime over phi is equal minus lambda. Another equation is minus R double prime over R square plus R prime over R is equal minus lambda. So then this one you can write like phi double prime plus lambda phi is equal 0. This is equation 2.1, lecture number 2. Whatever this minus will be plus, you can write this equation as R square. If you multiply to R also, right? R square R double prime plus R prime minus lambda r is equal 0. This equation is equation 2-1, lecture number 1, okay, lecture number 2. Right? What about this equation? What you can say about this equation? This equation is equation 3-1, lecture number 3. Name of this equation is Cauchy-Euler equation. It is a Cauchy-Euler equation, not Bester. Don't mix. This is Cauchy-Euler equation. Okay. So for this equation, I have a condition. It must be periodic because you see, the function u must be periodic. U will be periodic. U must be periodic, right? U will be periodic if phi is periodic, right? Because phi depends on phi, not r. So phi 2 plus phi plus 2 pi must be equal phi, right? Phi, because u is periodic. So now I can bring this condition here. Phi plus 2 pi equal phi. So then what will be the solution of this Sturm-Liouville problem? So you needed to find those values of lambda for which equation 2-1 has periodic solution. Remember about 2-1. The solution of 2-1 depends on sign of lambda. If lambda is negative, it is hyperbolic functions, right? But hyperbolic functions are not periodic, so lambda cannot be negative. If lambda is 0, then equation 2-1 has a constant solution. So it is periodic. So it means you have many functions. Let me say lambda n is equal n squared. N is 1, 2, 3, etc. So phi n will be like this. Phi n solutions, phi n is equal phi n cosine n cosine n 0 also includes, okay, cosine n phi plus bn sine n phi. Those are periodic functions, a n, b n, any constant, and if n is 0, phi 0 is equal a 0, is constant. So we have many functions like this. A n cosine n phi. This is for n equal 1, 2, etc. For n equals 0, we have a 0. These are eigenvalues and eigenfunctions. So what about Cauchy-Euler equation? So what is this equation, Cauchy-Euler equation? Now I can substitute lambda. It is plus r prime minus n square r is equal 0 because lambda is n square. We find from first one. So remember the solution of this equation? Let me remind Cauchy-Euler equation. It was like this: a square x square y double prime plus bx y prime plus cy is equal 0. That was the Cauchy-Euler. Remember, it depends on ABC, right? ABC. So this is okay, right? This is ABC, right? It is Cauchy-Euler. Okay. It depends on ABC. So you have to write characteristic equation. What was the characteristic equation?
Sir, sorry to interrupt, sir. Someone wants to enter the class.
Someone wants to enter the class. Okay, admit. He's not. Can he try again? Okay, he's in, or he's in or not. Okay, now you cannot see. Yeah, he's in. Okay. Okay. Let's just not go to this deeply for this. Just maybe I'll just show you. What we do is very simple. For this, we have a Cauchy-Euler, right? What was the solution? For this equation, you can write characteristic equation. So solution you can write like this. If n equals 0, then solution will be, we have three cases, remember, depending on the solution of root of characteristic equation. So somebody asking. Okay. Let me do all done. So done, okay. So if n equals 0, then function r0, r will be equal. So how to write? Let me write like this. C. Okay. Some constant. Okay, let me just write 1. It will be 1, actually. We should write like this. C01 plus C02 ln x. If you see lecture, you can see when n equals 0, we have this one. Okay. But for others, solution will be Rn. R is equal. So will be equal C n1 Cn1 r power n plus Cn2 r power minus n. So this will be solution for n equal 1, 2, 3. Just check with lecture number 3. So when n equals 0, you will get this solution. Then this is solution. Now, what we say is that C20 and Cn2 must be 0. Must be. Why? Because if it is not, if this coefficient C02 is not 0 and this one also not 0, then what will happen if R is equal to 0? This point is R equals 0, right? R equals 0 belongs to our plate, right? To our plate. But R equals 0, in R equals 0, because, let me write here, because when R equals 0 in my plate, 0, this, because ln R, right, this is correct, ln R and R minus n infinite, okay? So it's not possible. Heat cannot be infinite, right? That's why C02, Cn2 must be 0, because when you say R equals 0, if you say these two constant, C02, Cn2 not 0, then what will happen? If they are not 0, then Rn 0 will be equal to infinity, because you have here minus n, 0 power minus n, or logarithm 0, it's infinity, right? So it cannot be, right? So that's why we say these two constants must be 0. Then choose C01 and Cn11. Choose Cn1 as 1. So then what will happen? Your R0 will be constant, right? R0 will be 1. So you can say Rn for all n, Rn, R will be equal just R power n. So we will choose like this. When constant Cn1, 0. So for n equals 0 including. When n equals 0, you have 1, function 1, right? You see, check. So if C02 is 0, you have only C01, which is 1, right? The same. This term is 0, Cn1, which is 1, R power n. So we have R, we have 5. So then we have many functions, U functions, right? U. So we have a UN R5. What is UN R5? It is equal R power n, AN cosine n phi plus Bn sine n phi. So we have many functions like this. Okay. then all of them, all satisfying equation, you can verify it's satisfying steady-state equation, plus all of them are periodic. This period equal 2 pi, right? 2 pi periodic. So, but our problem has boundary conditions. So we find many solutions of this equation, which is periodic, but we have now to check this condition, right? UC phi must be equal to F phi, right? So then the solution we will search UR phi as, we will search solution as combination of all these UR phi is equal R sum. Let me separate zero term because zero term, we don't have B0. We don't need B0 actually. We don't need B0 because when n equals 0, the sign is 0 already, right? So let me write like this. When n equals 0, I have A0 plus sum n from 1 to infinity Rn A times cosine n phi plus Bn sine n phi. So this is the shape of the solution. So now use boundary condition. What is boundary condition? UC phi is equal F phi to find An and Bn coefficients, right? We use this boundary condition to find An and Bn, right? So let's write what is UC phi is equal A0 plus sum n from 1 to infinity. So what will be C power n, right? An cosine n phi plus C power n Bn sine n phi, right? So this is actually must be equal to F phi. So what we see here, it is Fourier series, right? Fourier series. These coefficients must be Fourier coefficient of F, right? What was the formula for A0? A0 will be equal, what will be A0? A0 will be equal 1 over 2 pi integral from 0 to 2 pi F phi d phi. You can very easily check. If you just integrate this, both sides, on the left side, you will have integral of F phi, right? When you integrate, integral of cosine, integral of sine will be 0. And you have here A0, integral of A0, 2 pi A0. Then you will get this A0. And An coefficients will be equal, because they have a Cn here, right? Cn will be equal. So what will be An? An will be equal 1 over Cn times pi, integral from 0 to 2 pi, right? From 0 to 2 pi, okay, from 0 to 2 pi, from 0 to 2 pi, phi, cosine n phi, d phi, okay, d phi. And similarly, we can write Bn coefficient. Bn is equal 1 over Cn pi, integral from 0 to 2 pi, f phi sine n phi d phi. So we find the solution, right? What is the solution? Solution is, this one is the solution, right? This is the shape of solution. This is the solution. Then these are formulas for the coefficients. Any questions before we go to next topic? Okay, you can think about your question if you have any. Let me now change my plate like this. Is it circle or not? This looks like circle. Let's see circle. Circle. So now our plate is ring. Not circle, but ring. Let's say this is x-axis. So let's say this is A, radius of small circles A, this is B, A and B. What will be formulation of the problem? It's still like ring is like circle, two circles. That's why equation will be polar system. So polar. So equation will be URR plus 1 over R, UR plus 1 over R square, URR, sorry, U phi equals 0. Equation is the same. Right? But now we have two conditions. Okay. So my plate is actually, this one is my plate, right? This is my plate. Plate has two boundaries. So boundaries, we have two boundary conditions. Heat maybe here is equal F phi. On this boundary, maybe it is G phi, right? Then both boundary conditions will be non-zero. But we can split problem into two problems and make each one is with 1-0 boundary conditions. That's why I will skip this just again. When you have, so we have actually two boundaries conditions. So we have like this, when R is A, phi is equal G phi, okay? And another boundary condition is U, B, when R is B, phi is equal F phi, means your plate is heated in this internal circle by temperature is equal G phi and external is F phi, right? Then you need to find the steady state, right? So I see this, in this case, both boundary conditions are non-zero, but we can split it into two problems like we did in first class about steady state, then bring it as one, at least one will be zero, right? We will have two problems. Each will have 1-0 boundary conditions. Let me say, let it be this one of them. The solution is very similar. Solution is very similar. Let's say UA phi is equal 0. So we have 0 on this line. We have 0. So then equation, two boundary conditions, 1-0 boundary condition, right? Then we have, of course, it must be periodic. Phi plus 2 pi is equal U R phi, because U R phi, R phi is the same. If this is R phi, then if you change phi, this is your phi, this is R, right? This is your phi. Then if you change phi to phi plus 2 pi, then it will be the same point, okay? The same point. Okay? The same point. So this is a statement of the problem. Equation, two boundary conditions, and condition that function must be periodic. So what will be? If you split it as above, you will come to the same things. So if you do search like this, U is equal R, phi, you will get the same. Phi will be, phi 0, phi will be, is equal, the same as above, equal 1. Phi n, phi will be equal an cosine n phi plus bn sine n phi. So the same thing. So lambda n is equal n square, right? Then the same thing for R function. So R0 will be equal C01 plus C02 ln R and R is equal Cn1 plus, Cn1, the same thing as above, Rn plus Cn2 R power minus n. But we cannot say now that C01 and C02 and Cn2 will be 0. Not necessarily, because center is outside of this is center. R equals 0, this point. This point is not in my plate, right? We don't have R equals 0. R cannot be 0. Minimum R will be 8, right? So we live like this. We cannot say, we cannot conclude that C02 and Cn2 will be 0, not because R cannot be, because R is actually from A to B, right? R is from A to B. We cannot say this coefficient must be 0. There's no problem with R function, right? Now, what we say, we have many functions, UN, R, phi. It is product of Rn, so Rn and phi. Let me write, so what we have here, if I write like this, what is the UN? UN must be, let me write UN, U0 separately, U0 R phi right here. So what is UN? It is Cn1 Rn plus Cn2 R minus n, An cosine n phi plus Bn sine n phi. So we have like this, right? Like this. Okay. And U0 is equal C01 plus C02 ln R, right? It should be multiplied to A0, but A0 is any constant, right? So I can write like this. It is equal what? It is equal A0 C01 plus A0 C02 ln R, but actually this is when A0 any C01 any, then the product also any. It's also any. So this I can write like this. Let me write like this. A01 cap plus A02 cap ln R. So because A0 any, C01 any, then it's a product of any constant, right? So it's any constant I denote by A01 cap. Not cap bar. Okay. So what we can say about these functions, all of them satisfying equation, and all of them are 2 pi periodic. That's what we can say. This we can state. Okay, now let me use zero boundary condition. First, let's use zero boundary condition. What is a zero boundary condition? What was the zero boundary condition? It was a U A phi is equal 0. Remember? U A phi is equal 0, right? So if you use this, what will happen? For UN, let me use it for UN. UN A phi is equal C1n AN plus Cn2 A power minus n, right? An cosine n phi plus Bn sine n phi must be 0, according to the boundary condition, right? Must be 0. So this is actually, second bracket is a function. So what about first bracket? It is a constant. We have constant time a function, must be 0. So what is our conclusion? Constant must be 0, right? So C1n an plus Cn2a minus n must be 0. So from this we can find the relation between C1 and C2, right? So from this it follows, for example, Cn1 is equal, what is the Cn1? Cn1 is equal minus Cn2 a power minus 2n, right? If you divide to an, you will find this one, right? Clear? We find the relation between C1 and C2. Then I can substitute to un. So what is my un? un R5. un R5. What was un R5? It was C1 Rn plus C2 R power minus n, right? Let me write like this. Okay, let me first write like this. Cn2 R minus n a n cosine n phi plus bn sine n phi equal, now I will substitute C1 is equal to this, right? C1 is equal to this. So what will be this? If I substitute here, okay, let me substitute this. What will be? Okay, Cn plus 1 is equal to this. You will have this one minus Cn2 a power minus 2n Rn plus Cn2 R minus n an cosine n phi plus bn sine n phi equal. So then I can take out this this constant. Let me take out this minus Cn2, right? The same. And then I have Rn a power minus 2n plus minus R minus n, right? R minus n. Then I have an cosine n phi plus bn sine n phi. So then I can bring this one inside here, right? If I bring here, this first will be this function Rn a times minus 2n minus R minus n. So if I bring this here, you will have an times minus Cn2 cosine n phi plus bn minus Cn2 sine n phi. So now I state again. So what is an? An is any constant. Cn2 also any constant. So this will be any constant, right? Any. Let me denote it by an bar. The same, this one, let me denote by bn bar. Then I have this one. Rn a minus 2n minus R minus n. So I have an bar cosine n phi plus bn bar sine n phi. So an bar and bn bar, any constants, right? So this is un. Not now. Let me write now u0, right? Where's my u0? U0 I already written. Okay, u0 we already have. Let me just copy here u0. This un, right? u0 r phi was equal a0 bar plus, I said a0 bar, and let me say b0 bar. Oh, I said, okay, let's say this is b0. Let me this a0 and b0. No, not b0. Okay, leave it like this. a01 and a02. Okay. a01 plus a02 r ln r. So we have un like this, and we have u0 like this, many functions. Now we will search solution. Now you have many functions. They satisfy equation, zero boundary condition, right? So now this all, let me say this un, right? This un. So all of them, now I can say all of them satisfying satisfying equation 2 pi periodic and satisfying condition u, what was the condition? UA phi is equal 0. You can check, they all satisfying this condition. UA phi is equal 0. No, we don't use for u0, okay. So for u0 we need to use, yeah. For u0 we didn't use so far, let me use for u0. For u0 so far we didn't use this condition. Okay. So if I use this condition, UA phi is equal 0 for u0, then what will it be? U0 A phi is equal A01 bar plus what is this? A02 bar ln A, right? ln A must be equal 0. So from this you can find that A02 is equal, A02 bar is equal, what will it be? Minus A01 over ln A, right? If you find from here, A02 is equal to this, okay? Then U0 is equal, U0 R phi is equal, if you substitute here, is equal A01 plus minus A01 over ln A, ln R. So this you can write like this, it's equal, this is equal A01 1 minus ln R over ln A. ln R, ln A. Okay? And it's clear that U0 also satisfying zero boundary condition. If R is equal A, then you will have here ln A over ln A will be 1 minus 1, 0. So we have many functions, this function and U, all of them satisfying. So let me bring UN here now. UN has this shape. Okay. UN. This is U0 and UN. UN R phi is equal. What was UN R phi? So R times A power minus 2n minus R minus n. So A0 bar, AN bar. AN bar cosine n phi plus bn bar sine n phi, right? Like this. Okay, let's check. Yeah, like this. So we have these functions u0 and un, all of them all satisfying equation. So what else? So equation, zero boundary condition and periodic, 2 pi periodic, and satisfying equation, zero boundary condition, U A phi is equal 0. All of them satisfying these three conditions: equation, periodic, and satisfying this zero boundary condition. But our problem has this condition. We have to check this last, not this one. We have this condition, right? Non-zero boundary condition. So now, solution, we will search U R phi, which is solution of problem, as follows. Okay, UR phi is a combination of all of them. First, I will write U0. What was U0? A01, A01 bar 1 minus ln R over ln A, right? Plus sum n from 1 to infinity, R power n, A power minus 2n minus R power minus n, right? Then AN bar cosine n phi plus Bn bar sine n phi, right? So this is the solution or shape of the solution. So to find, use last boundary condition, use non-zero boundary condition, use this condition, U B phi is equal F phi to find or to identify A01 bar, AN bar, and Bn bar. We can find all these coefficients using this condition. So what is the UB phi? If you substitute B, so it will be A01 bar times 1 minus ln B, right? ln B over ln A, right? ln B over ln A. Okay, ln B over ln A plus sum n from 1 to infinity. So what will be this? When R is B power n, B power n, A power minus 2n, minus R power minus R, no, B power minus n. This is constant, right? So we have AN bar cosine n phi plus Bn bar sine n phi should be equal to F phi. So this is the Fourier series, right? F phi, Fourier series. Now we can find all coefficients. So what will be this coefficient? A01. A01 bar is equal 1 over, this constant is coming here, ln B over ln A times 2 pi, right? Integral from 0 to 2 pi, F phi d phi. Okay, this is A0. And we have AN bars. AN bars are 1 over, what was there? Bn, A power minus 2n, minus B power minus n, times pi, integral from 0 to 2 pi, F phi cosine n phi d phi is A coefficients, and B coefficients will be 1 over the same thing, Bn, A power minus 2n, minus B power minus n, pi, integral from 0 to 2 pi, F phi, so sine n phi d phi, right? So we have formula for all coefficients and formula for the solution. This one is a solution, UR phi, and these three formulas are formulas for coefficients. Any questions? Okay, if no questions, let me just change the shape of the plate. Okay. Let's see, this is y-axis, y-axis. Let be the x-axis. Let be, this is portion of the circle. This is not circle. I can draw it. That's no. Not good. Let's say like this. Let's say it's a circle, portion of circle. Let's say this is like this. Let's say BB. So plate is this one. Plate is this is my plate. So now this plate is a portion of the ring. It is not whole ring, but portion of the quarter of the ring, right? So this plate has 4 boundaries. So we will have 4 boundary conditions, right? So 4 boundary conditions. So equation is the same. Let me write equation. Equation is the same. URR in polar system, 1 over R, UR plus 1 over R square, U phi is equal to 0, right? This is steady state equation. Now we have 4 conditions. One condition is when R is equal A. When R is equal A, U A phi is equal something, right? Another condition is U B phi is equal, so condition here. Okay, how I describe this condition is R is equal B, right? What about this condition is R is equal A, right? So what about this condition? This boundary, how I can write this condition? On this condition, phi is equal 0. So you are 0, so I will get condition here. Clear? When phi is 0, I have this. So what about this condition? This boundary? Phi is equal pi over 2. When phi is equal pi over 2, you will have this, right? So you have 4 boundary conditions. So this must be function of phi, this must be function of phi, this must be function of R, this must be function of R, right? Then plus must be periodic. U R pi plus 2 pi must be periodic. U R pi. So we have, this is our problem, right? This is our problem. Now I'm not writing what is equal. Equal can be anything. Can be here F phi, right? Or let's say G phi, F phi, right? So this can be F G H R. So what else? We have H F H G, but Z R, whatever, right? So we have 4 non-zero boundary conditions. You can split into 4 problems. Each one will be having 3 zero boundary conditions. We can split this problem into 4 problems. Each will be having 3 zero boundary conditions. That's why we'll solve only 3 zero boundary conditions. Let's say this is 0. Let's say this is 0. Just for similarity with previous one. So 0, we can always make like this, 3 zero boundary conditions. Then what will be difference from previous one? So we will do all the steps until, so let me just, in previous exercise, in exercise 2, we found many functions un and u0, right? Satisfying, remember? Satisfying equation, 2 pi periodic, right? Periodic, right? And satisfying condition u b phi, u a phi is equal 0. Remember? What was the, so we don't need to do the same thing again, but we can write. So we have many functions. What was the un? What is un? R phi is equal, as you remember, it was like this. An, right? No, Rn, sorry. It was like this. Rn, a minus 2n, minus R minus n, n bar cosine n phi plus bn bar sine n phi. This is for n equal 1 to 3, etc. So u0, our u0 was u0, r phi was equal like this. What was u0? We have a 0, 1 bar, something like this, right? So 1 minus ln r over ln A. So we find this function. So all these functions satisfying equations, the 2p periodic and satisfying this. Now, if you look our problem has, so we already have equation, right? Equation, this and this. Now, but we have 3 more. We have 2 more zero boundary conditions. Now I will use this, and I will use this, and last I will use this one. Okay? So let's use UR00. So what is UR00? So for U0, it's no change because U0 is independent from phi. So what will happen with UN? Use condition UR0 is equal 0. Let's use this. For U0, no changes, right? For U0, no changes. Because it is independent from phi, right? So what about UN? UN R0. So what is UN R0? UN R0 is equal, what is this? R n, A minus 2n, minus R minus n. I must say phi is equal 0. If phi equals 0 times an bar, because sine is 0, cosine is 1, right? So remaining only an bar. So this should be equal 0. So when it will be 0, this is a function of R, right? This is a constant. So our conclusion is that an bar must be equal 0. Clear? An bar must be equal 0. Then I change only un. So what will be un? Un has this shape. Where's my pen? Un r phi is equal. Un r phi is equal. So what? It is equal Bn bar. So Rn A minus 2n minus R minus n sine n phi, right? And U0, no changes for U0. It is equal A01 bar 1 minus ln R ln A. So we have many functions. Now what we can say about this? All of them satisfying. Now all satisfying. So equation plus the 2 pi periodic plus the satisfying this condition UA phi is equal 0, UA phi is equal 0, and plus U R0 is equal 0. Oh, yeah. So A0, sorry, U0 is vanishing. Okay, which no changes U0 is not correct. We have to check it for U0 also. You see, we don't say U0 no changes. But what will be condition for U0? No changes, of course, yeah. But what will be? You see, it's interesting. I said no changes, but I must find A01. So what is this? Use this for U0, for U0. So U0 R phi, it's equal A01 bar 1 minus ln R ln A, right? It should be equal 0 when phi is 0. When phi is 0, it must be 0. When phi is 0, this must be 0. So this is a function, then A01 bar must be equal 0. You see? Because this is in the bracket, we have a function. No changes for U0, but it must be 0. No changes for U0, but it must be 0. So A01, 0. Then U0 is 0. So we don't have U0. We don't have U0. Let me clean here. We don't have U0. U0 is 0. U0 is 0. So we have many functions. UN, U0, 0. All of them satisfying equation and to periodic. So n equal 1, 2. U0 already 0. And satisfying these two conditions. Now I have one more condition, right? one more condition. Now use this zero boundary condition. We have one more. What the condition? R pi over 2 is equal 0. Okay, so if we use this one, so for this un, what will be? Un R pi over 2 is equal Bn bar R n A minus 2n minus R minus n sine n times pi over 2 must be 0. So what we conclude from this equality, you see, it's interesting. This is a number. Just my pen, I cannot see my pen. Oh, here. This is a number. This is a function of R. We don't touch this function. So, and we have a number here. So what we can say about second number? Sine n pi over 2. Can it be 0? It can be 0, right? It can be 0. If n is even. So if n is even, this is 0, then we can save b, right? We can save b, non-zero. Then we can save Bn bar non-zero, right? So when n is even, right? So if n is odd, then sine n pi over 2 is not 0. It can be either 1 or minus 1. It's not 0. So then Bn bar must be 0. No way. So Bn is 0 for odd numbers, right? So we find that Bn is odd number. So Bn is odd number. If it is odd numbers, then it must be 0. So we have many un. Actually here un is n 1, 2, 3, etc. Now I say that if n is 1, then b1 0. So 3 is 0. So then what I will say, I cannot save all, right? I only can save even. So let me write like this. We have many un R5, which is equal, let me write here, B 2n bar, okay, because only un I can save, times, what about this? R power 2n, right? A power minus 4n, I think like this, right? A power 4n minus R power minus 2n, right? Sine 2n phi. Sine 2n phi. Now n is 1, 2, 3, etc. So I can save only this, right? I'm just taking away all odd coefficients. So we have many functions. What we can say about this? All satisfying equation plus condition UA phi is equal 0 plus U R0 0 plus U condition. As it's not plus, just condition, plus condition. So U R pi over 2 is 0 and plus all of them 2 pi periodic. But my problem has one more condition, right? So now search UR phi S. So what is UR phi? UR phi is equal sum n from 1 to infinity b to n bar r to n a minus 4n minus r minus 2n sine 2n phi 2n phi. This form, right? So to find b coefficients, we use last boundary condition. What was the last? UB phi is equal f phi to find b to n bar coefficients. So to find this b to n bar coefficients. So then if you substitute, you will have this sum, which is u b phi is equal n from 1 to infinity b to n bar b to n a minus 4n minus b minus 2n sine 2n phi is equal f phi. Then you can find b coefficients because this is Fourier series. B to n bar equal 1 over is b to n a for n minus b to n pi integral from 0 to 2 pi f phi sine 2n phi d phi. So this is the formula for coefficients. Okay. So just I will give you some homework that will be last what we will consider now. Let's say your plate has this shape. Usually plate has shape like this. Let's say plate has this shape. X. So let's say your plate has this shape. So let's say plate has this shape. If you continue, this be A. Let's see if you continue, let's see, this is B. So plate is this one. It has a 4 boundary condition. So let be this angle is pi over 6 or 30. Let be this is a 60. So then how we write this problem? Equation, the same. URR plus 1 over R. UR plus 1 over R square. U phi phi is equal to 0. 4 boundary conditions, right? So let's say here we have f phi. Let's say we have here 0, 0, 0, 3 0 conditions, right? So u a phi is equal to 0, right? So u r 30, what is 30? Pi over 6 equals 0. U r pi over 3, it is a 60, 0. And u b phi is equal f phi. This is non-zero condition and periodic. U r phi plus 2 pi is equal u r phi. Just try to solve this as homework. It's similar to previous one, but only difference you have different angles, pi over 6, pi over 3. In previous was 0 and pi over 2. Okay, that's all for today. Any questions? Let me stop recording. If you have questions, please ask me.